Thank you for having me here and having the opportunity to talk about at least our perspective on the industry. I'm going to try to give you perspective on the semiconductor industry and sort of how you, kind of from the eyes of someone who kind of deals with it from the mobile perspective. And I would say mobile, by and large, tends to, just due to its scale, and increasingly, and certainly this is the case in 5G, because of the how much data it's processing and what needs to be done and where it needs to be done, it tends to pull architectures its direction as well. And I think there's some ramifications for your work, and hopefully I can provide that perspective. Okay, so if you look at Qualcomm, just a very quick introduction to Qualcomm, but we're about 30 years old. We didn't have a semiconductor business. We were basically trying to figure out how to use the initial, I guess it was really digital communications and Viterbi decoders, and how can we figure out how to apply those techniques? They tended to be used in deep space work that a lot of you probably even worked on. And was there a commercial application? We essentially found that through first generation of digital cellular. Then people moved to, we could put a computer in your pocket, and Qualcomm had to develop that muscle as well, the computing side. And, but I would say the first 30 years of the company's history was really about how do you connect people together. And can you put a computer in your pocket, and can you make things happen? Tremendous, I would say, business expansion as a result of having those very small amounts of technologies connect people. The next 30 years really are about how do we connect industries? How do we get a lot of different infrastructure and digitization? How do we enable that? And tremendous, I would say, spreading out of the funnel of the technologies that have come from mobile. And as a result of that, what you've seen, if you were just going to take a look at the semiconductor industry from the foundry perspective, the semiconductor part of the semiconductor industry, you'll see that mobile tends to be the thing that sets kind of what node you're using, who's going to the node first, and even the structure of the foundry industry. And you're going to have Tom will come up, I think, and have a great perspective on that. But what's happened for Qualcomm, certainly, is we used to be a node laggard. And we would get into the node after the graphics guys were in the node. And then we would come in later and essentially try to push everybody else out because we have a lot of volume. But we didn't really care too much about the transistor. We come in 2 years late, maybe 3 years late. That doesn't happen anymore. Today, what happens is not only do we want to be 2 or 3 years late, our requirements are driving what the transistor design is, and it probably will never change. That's going to stay forever now. Kind of why is that? It's really just this combination of connectivity and processing together. You can put it in your pocket, and you have a tremendous amount of things that you can now do directly where the data is that you couldn't do before. For us, it's basically meant that we've had to generate a lot of different skill sets. So the heterogeneous computing aspect of it, we tend to have. So we tend to, and we did not have this before really the smartphone, but you have to have graphics, you have to have DSP, you have to have all of the things that display and move around pixels in a phone. You have to have, which is ISPs, and all the video work. And then increasingly more and more specific AI engines that allow you to make decisions on the data right where the data is. So if I look at 5G and AI, well, first of all, kind of talk about 5G. It's different than some of the other generations of cellular, and by and large, it's different because it connects everything. It's the first time cellular was designed to not only provide, what we call more G So basically for the cellular operators, there's a huge benefit to moving to 5G, primarily access to spectrum and lower cost per bit. But it's purposely designed from a security, latency, IoT point of view so that a lot of new industries can take advantage of cellular really for the first time. And that's a big deal just for 5G. But it also means that the future of AI will be really determined by the coupling of AI and 5G together. So the way you can think about it is there was a first generation of AI, which is really in the data center. And because the tool sets were very, were available primarily from the GPU folks, that's really what was used. That was the kind of the hammer that was available for the nail. But in the future, what you're going to see is, I think, a lot of these heterogeneous engines being applied to that problem. But you got to have 5G right next to it. And so we're in a position to do that. We're doing a lot of work to make sure that that's there. And there are some implications for, I would say, the rest of the industry. Okay, so I talked a little bit about this already, but really 5G is driving transformation in the industry. So what does that really mean for people? So if you just think about what is the trend in business that's changing people's businesses, it's really digitization. So if you look at healthcare, you look at industrial companies, you look at basically any company, they've all got a big data strategy, okay? Most of that big data that's interesting and has high value will eventually have some component of it produced, and hopefully a large component of it produced, by something that was connected with 5G. And that's where you get this big transformation that occurs. And probably the first time that we've seen such a large economic impact of 5G outside of the cellular industry. And I think, we commissioned a study, and I think it was something like in 2035, you have the goods and services from 5G. I think they're like $12 trillion of global economic impact. Obviously, much more than the hardware sales. I wish the hardware sales were actually close to that. It would be great. But it's not. It also creates something like 20 million jobs. So, when people talk about, having a jobs agenda, they should think about 5G and making sure that the U.S. is leadership in 5G and make sure that we're driving it forward, not only from the technology point of view, but the application of 5G. And that second part is a very important component. It's sort of how do you take advantage of things first, because whomever builds the scale in those industries will actually set the tone and the standards for the rest of the world. Okay, this is a slide that I know some of, certainly one ex-professor of mine in the audience will be very happy about, which essentially says 5G is kind of the first time that the RF guys are back in charge. And that's because we've basically reached the Shannon limit on everything else. And so we've made a lot of gain in coding, and the only way to get additional gain is to essentially have some really awesome antennas and to use them exactly right. Now, why are we able to do that in the commercial domain? I think a lot of people in this audience have a reason to celebrate that. It was a lot of the work that really DARPA funded on phased arrays and transceivers, really, for reasons that you know well why it was being done. The benefit of that was that we now know how to use those technologies, and more importantly, we even have people that know how to use and design those technologies available at the time when the industry needs it to create the gains that are possible by using these dramatic antenna techniques. So anyway, I think it's a great time to be an RF person and a millimeter wave person in the industry, because it's really important. So there's another aspect of that as well, which is as you have these smart antennas and you have these antennas that are being used, just massive amounts of MIMO, in some cases across across different sites, there's a lot of computing being done to manage those antennas, and it has to be done obviously in real time and directly where the antenna is. So it's another sort of ramification of mobile pulling computing and pulling the semiconductor industry toward its unique, its unique requirements. Okay, I think people know this already, but we used to have to tell people 5G will actually work, but now it's deployed, so you can just go and take a look at it. But the reality is there's pretty good real world gains on 5G, particularly where there's dense deployments, which tend to be where people want to digitize information. It tends to be where people are, of course, and those where the gains are. Tremendous benefits in terms of capacity and latency, and of course your ability to enable new requirements. Okay, I mentioned before that mobile is something that will, the combination of 5G and AI is something that will bring together, really pull AI into a different area. Just to give you a kind of a figure of merit, just today, about 10% of our, what we ship has AI or a dedicated AI engine in it. If I move that forward to 2025, 100% of the things that we have will have some form of AI engine in it. And there's a lot that people talk about. I joke around that AI has kind of become the new gluten-free. So everyone talks about it, but nobody really knows what it is. You can go on YouTube, you can look it up, there's some really interesting videos. No one knows what gluten is, actually. But AI has somewhat of a similar bent sometimes. And for us, it's just a specialized processing engine that allows us to take advantage of some data. So a data-specific computer, but it has to be architected for it to be useful in a way that can be used in your pocket or on the front of an antenna array or whatever. And so it has to be architected for low power. That's a completely different design point than what you would use if you were coming at it from the data center. Same thing happened in GPUs. If you noticed, the architecture of GPUs in the data center, or in the PC, or in the applications that are plugged in, tend to diverge from that which is used to on a handheld device. Same thing is going to happen with AI. Okay, a little point about how the data will be spread around, at least how we think about it. So, and I'll just use the really basic analogy, which is there's a reason why your hand moves away from a hot plate before your brain knows about it. There's certain data that you have to make a decision very rapidly because the data is relevant in real time. But you don't have, and you don't necessarily have to have all of the processing for that data done, in your hand. But you have to have communication between your hand and your brain, on a regular basis, but not all the time. And that's essentially how the processing will be worked. So there's a real need for cloud players and device manufacturers, or sort of, the edge of the internet, to coordinate the architecture of how big data and AI works. And, that's really how it will work. So partnerships, collaborations, frameworks that allow that to happen will tend to be, I think, what will happen long term for how these things work. And you see that, of course. There's also some consumer reasons why you have to make decisions out in the kind of edge of the internet. And it's because people are creeped out by sending their information back, basically. So if you look at a security camera, people don't want to have the really specific parts of a security camera. The AI that does face recognition might recognize your kids, might recognize whomever. They don't want everybody in the world to have access to it. So by architecture, we have to have that done in our chips. Okay, I mentioned this already a bit, but the fact that there's so much AI and there's this transition to this mobile design point of AI just means that the architecture of the device that does the AI is going to change. We think that's a great thing. It basically means that power and thermal efficiency are very important. I think what it means really is that you have more specialized engines, and engines that are more specialized for a class of applications or use cases, or data sets, I guess, than you would have for more general purpose parts. Same thing happened to us in other areas. I mentioned the GPU, but that tends to go there. What that means practically when you're looking at the industry is that there is no one-size-fits-all solution, at least at the device level, that we expect to see. I talked about this a little bit already, but if you looked at kind of our transition through the semiconductor industry, our transition being the company's transition through the semiconductor industry, there are a couple of really important, I would say, transitions. And you could see it by where we had to have expertise to be successful as a company. So the first one was you just had to have some ability to do ASICs, to implement things like Viterbi decoders and all of that. But if you looked at a cell phone, you had a lot of people that understood things like FM radios, and they understood about PA saturation and all that kind of stuff. But the real center of mass of the semiconductor industry was in the PC space. And people talked through languages like Moore's Law and things like that. When the smartphone came out and it got combined with OSs and really 4G really hit it really hard because of its ability to provide data at a speed and cost. What you saw was that the semiconductor industry really moved to the point where mobile was the one that was driving the designs. Also, mobile tended to have such high scale that it tended to create the structure of what we would, the fabless industry. So what does that really mean? What that means is if you wanted to see who could invest in the leading node of a foundry and what the design point or the design envelope of the solutions would be, you basically looked and you saw where is Qualcomm going to be and where is Apple going to be. And if we're both going to be in the same foundry, that's going to be the design point. And so we would have to try to figure out where we're all going to be. And that still exists today. If you look at the industry, that tends to be what determines the structure of it. It's no longer what's happening in the PC space or in the other spaces. As you move forward, I don't think it ever goes back. I think it's whomever is involved in 5G will, of course, keep that position in terms of where the foundry, the foundry's design point, and even who can remain in the foundry, that's really going to be determined by who has access to those end markets. We obviously think we're going to continue to be in that position, and it impacts our strategy, probably should impact some of the thinking of this room as well. Okay, the other thing that I think that we see is that along with the scale and the impacts of mobile scale to our manufacturing partners and the availability of the design envelope associated with that, if you look at our designs and you look at anyone's designs in this industry, they're really moving more towards special and distributed machines. So you don't have a general purpose computing solution. So for example, we have many different engines that run on the chip that are optimized for the particular use case. So, something for video, something for, we have our own custom DSPs. We have that for a reason. We actually run our protocol stack on the DSPs. And that trend of having the right computing element for the use case is, I think, the way that it goes. You're seeing that trend go back into the data center, and that's why you see specialized engines being used if they're going to use it for inference or training or whatever. And it's those specialized design points versus a generalized architecture we think are going to be the solution moving forward. That's just because power and performance tend to be so important. Moore's Law. So I get asked a lot, what's your impact to the company on Moore's Law? And quite frankly, I kind of glaze over for a little bit because it's sort of a discussion about things that in many respects don't matter. What does matter is if you're in the mobile industry and you're in the computing aspects of the mobile industry, if you're not at the leading node, you're not going to remain in that industry. So you can talk about what the curve is. You can figure out whatever the exponent that you want to put on the whatever curve you're going to fit to it. But the reality is, if you're not in the leading node, you're not going to be there forever. And so we always do two things. We make sure that we're there, and we make sure, at least for a portion of our designs, and we make sure that we have the scale that allows us to afford to be there. And that's basically Moore's Law for us. Okay, one of the reasons why that's the case is the peak rates have gone up like crazy. So the peak rates on cellular, tremendous innovation at the system level to get the peak rates up. And because of that, you got to have a lot. You got to process all that data. So you got to have access to a high-power computing solution, not just because of what you're going to do with the data, but to even get the data from the radio. And that's not coming back either. So that's going to continue like that. I mentioned this already, but essentially, you got to have to be in the mobile space. At least my view, it's a decathlon. It's not just one sport. You have to be good at many different things. One of those things is actually your ability to partition things and your ability to do packaging. So let me talk a little bit about that. So there's innovation at the architecture level, there's innovation at the transistor level, there's innovation at the systems level. There's also innovation in packaging, partitioning, and interconnect. This is an area where I would say 10 years ago, when you would visit universities, you would try to figure out what is the design, who are the people, who's the professor that's producing the person that knows how to be a packaging engineer for a company that's trying to figure out how to make packaging an architectural design element. And if you look at the background of those folks, it's a weird mix, right? That's an area which I think is interesting and will be increasingly important moving forward. The ability to do, repartitioning and the mechanical, chemical, all of the things that are required in order to give the tools to the designers to enable that to happen. Another aspect is memory. So I have a couple of slides on memory. The takeaway, quite frankly, is memory and computing are intertwined, definitely intertwined in the mobile. There are implications from the design perspective, but there are also implications from the supply chain, business model. I would say if I was a strategic planner for not just a company, but for a country, I would look and I would say, you really can't be strong in computing unless you have a strong relationship with memory, including the technologies that allow you to talk to memory so that it can be integrated very, very closely to where the computing is done. And this chart essentially tries to say, hey, there's some architectural elements of that which allow us to get some advantage. We are a proponent of that. And any way that those technologies move forward, we find that very interesting and enables new industries to develop, actually. Similarly, you can take that paradigm and throw it back into some other existing industries and find some advantages. So if you look at the kind of compute in memory aspect of devices and architectures, it does allow us to produce just more operations per watt. And that's a significant kind of benefit from working at that level in the mobile space. That allows us to go into other industries, and you'll see more and more from us on that topic. I talked about packaging, kind of packaging at the SoC level. But there's also evolutions happening at the device level, meaning if you opened up a phone and you were to look inside of it, there's really been a tremendous amount of innovation as to how the packaging is coming together. That will continue. It will have and continues to have ramifications for our business. We have the ability to really include more and more of the BOM of the phone. That there are some good technical reasons why that's the case, but there's also a good opportunity to enable people to use technology without having to have all of the expertise to allow the RF expertise, the layout expertise, the ability to do just very exotic mechanical and thermal design. We can do that now through some of these technologies that are now available and deliver much bigger technologies to our partners. At the time when more and more partners that don't have the traditional sophistication of a phone vendor in the areas of the phone are wanting to get access to 5G. That's enabled really by some of these technologies. All right, I talked about the leading node. I've stressed this probably 3 or 4 times, but I think it's worth hearing again. The combination of 5G and AI really bump up the amount of computing that's required. The fact that 5G is sitting there and takes all this computing requires a tremendous amount of computing just to operate the radio. You have to make sure that you have access to the leading node. If you look at kind of the world today, there aren't a whole lot of sources for it at scale. And if you haven't done it, you can do a calculation of what would be just the total wafer volume that would be associated, let's say, with 40% of the, just take the mobile market, figure out what a die size is, multiply it by some typical size, figure out the wafer volume is, and then try to figure out where in the world could you get that amount of volume. And that's the problem that you tend to have, but it's also the opportunity, I think, if you can tap into that, you have a great opportunity to leverage that scale. But that's really the problem for us, is how do we solve that problem? And then as you go to 5G, the die sizes improve, even they increase a lot. So it's a bigger problem for us. Let me talk a little bit about security. Security, another big element of our portfolio of technologies. The way I think about security is it's a necessary thing to make sure is integrated in the chip. The data has to be secure as immediately as it's created. And if we don't do that and we don't convince people that it's there, certain industries won't develop. And this is one of the areas where just having technology is not enough. The technology is actually there. So for example, for us, we have already integrated in the equivalent of a secure element is already part of our chip, including the certification. All of that certification we now have, we just recently announced that on our Snapdragon platform. But what is going to be interesting will be how do you get, what is the standard for wireless healthcare? What is the standard for securing data that can control a car? What are all of these things that now are mission critical that are enabled by 5G? Those industries won't develop by just throwing technology in a chip and doing it. There needs to be some certification process. There needs to be some, quite frankly, needs to be some legislation to make sure that we know how to control these technologies and make sure they're secure, or else the industries won't develop. So there's some work there that's not technical that I think we all need to pay attention to a little bit. Okay, this is one of my last slides, but kind of how our perspective, I guess, on what is maybe the U.S. semiconductor industry. First, I think the kind of public-private collaboration is very important. I mentioned a big dividend to 5G from some of the early work on and early funding of phased arrays and all these transistors. I'll tell you kind of an interesting story, at least I'll do it very quickly. I left University of Michigan because I didn't think you could get paid to do millimeter wave transceivers. And so I ended up going to Qualcomm, actually almost exactly 25 years ago. And my advisor, who was sitting right over there, told me, that's like an IF frequency you're working on. Why are you working on those things? And I said, because they'll pay you. And now here we are 25 years later in Detroit talking about how millimeter waves are really what we really need to do back in there. There's a reason that's the case, and it's an example of the public-private collaboration, and you have to keep going on it. Very important. The industry R&D. We don't generate people who want to go into semiconductors the way that we did 30 years ago. And that's not a great thing. When we go talk to universities, a lot of times we tell them we want all of those, we want designers of circuits, we want systems designers, we want the things that are what you would call the core curriculum. Keep it coming. We like it. Global ecosystem collaboration, I think that's a reality for us. It basically means our supply chain is going to be an international supply chain. We have to be comfortable that it's secure. We have to be comfortable that it can survive geopolitical changes. We have to be comfortable that it can survive weather. And our requirements are too big for it to be any other type of design. And so we have to have a global ecosystem collaboration, or else the industry doesn't thrive, at least at the scales in which we would need it to do. We obviously think IP is very important. We sometimes get some commentary on our IP policies. But the ability to create IP and to protect it, both secure the physical IP when you're dealing with partners, but also protect the patents and the rights of inventors, very important to keeping innovation going. And then, of course, the skills. I talked a little bit about generating things, but the skills are very important. I'll leave one aspect. I talked a lot about kind of the hardware aspect of it. Most of the people who work at Qualcomm are actually, you would consider them to be software people. Software, secure software, the ability to produce software at scale, very important component about delivering the systems that are made possible by all the things that I talked about. So with that, I want to thank you for having me here, and thank you for your attention. Thank you.